Today we're going to have a big change of pace, but before we do, let's look at where we've been. So we learned about forces, fields, voltages, and energies, and then the formulas that connected those ideas. We applied them to capacitors as accelerators and deflectors. We saw how in the oscilloscope we fired the electron with one capacitor and then we deflected it either horizontally or vertically or both with another set of capacitors. Okay, we figured out how long it would take a particle to move from one place to another between the two plates of the capacitor. And today we want to change gears and look at what happens when charges are actually in motion. Some weird things begin to occur. Okay, so I'd like to start with an idea that we never got a chance to really explore in detail last year, and that was the idea of a magnetic force. This is an idea, though, that I'm sure you guys have touched upon somewhere along the way in your schooling. And that is the idea that magnets have a north and a south. They're kind of like a plus and a minus for charges. They're arbitrary in the same sense, but don't think of a north as a positive. It has nothing to do with a static charge like we had with our previous forces. But we still have the same idea that if you have a north and a south that are close by, they're going to attract each other. And if we have two norths that are facing each other and close by, they're going to repel each other. So it's the same basic rule, except now instead of applying it to positive and negatives, we're applying it to norths and souths of a magnet. Okay, when you talk magnetic field instead of electric field, we talk about using the variable B. So whenever you see B in one of these equations, a capital B, it stands for magnetic field. Magnetic fields are measured in a unit called Tesla. Okay, and usually the numbers are going to be rather small. If you saw a magnetic field of 3 Tesla, that is an extremely large magnetic field. Most times you're going to see much smaller magnetic fields, maybe even as small as millitesla. Okay, magnetic fields measured in Tesla, they point from the north to the south. Just like electric fields point from plus to minus, these point north to south. So that's our B field between these two magnets. If we place a charge in that area between the two poles of the magnet, that is, we place a charge in the magnetic field and let go, nothing happens. I know that's disappointing, but it's a really fundamental idea that a charge that is at rest will not be affected by a magnet. However, if we put that charge in motion, that is, we use capacitors to accelerate an electron and then have it enter into a magnetic field, now the same electron that felt nothing when it was at rest will feel a magnetic force when it's moving. The faster it moves, the greater the magnetic force. So you can see the formula here. Magnetic force, brand new force, we haven't used it yet, is equal to the charge. That's the charge that's moving, how fast it's moving, and you can see if it's at rest, we'd have a velocity of 0, which is why we get no magnetic force, okay, on a static charge, multiplied by the strength of the magnetic field. So again, charge, velocity, magnetic field gives us force. You'll notice how the field deviates from the original path, and you might ask, what direction does it go? It's not as simple as it was with charges, where the charges we could easily say, oh, this is a negative plate, positives are going to go towards it. Negatives are going to go away from it. It's not that simple with magnetism, because charges have plus and minus, and magnets have north and south. They're not equivalent, so we need a new rule, a new way of figuring out the direction of the force. Okay, so we can calculate using the formula we just had and we can get a value for the force magnetic, but what direction is it? Okay, before we talk about that, I want to make sure you know that these problems, you're going to have to think in 3 dimensions. So forget about just X and Y. Think also about Z, which would be coming towards you. So on this board, we would have X, we'd have Y, and Z coming toward you. Notice how we draw it. We try to represent 3 dimensions in a 2-dimensional space. And when we are actually drawing arrows, right, left, up, down, easy. Here's how you represent the 3rd dimension using vectors, using these arrows. The X is like the back of the arrow, like where the feathers are. This represents when something is going away from you. So if you're watching this now, this controller is moving away from you. You represent that with an X. A dot represents when it's coming towards you. Okay, so dot coming out of the board right towards you, X going into the board and heading toward Miss Dare's room. Okay, so here's the rule. To figure out the direction of the force, you put your fingers pointing in the direction of the magnetic field. You point your thumb in the direction of the charge, and it's important when you do this to form a right angle between your fingers and your thumb. And then your palm of your hand will push toward the direction of the force. Okay? So again, use your left hand if it's a negative charge, right hand if it's a positive charge, and this is the rule to figure out the direction of the force on that charge. Okay, so let's try one. Here is a positive charge, so you're going to use your right hand. This is the magnetic field it's being shot into, and you can see its X's, which means the field is pointing toward Miss Dare's room. That means the north of the magnet is on this side, and the south would be over there. The magnetic field points toward the south. Here comes my positive charge into this magnetic field. And what's going to happen again is we take our right hand, we point our fingers in the direction of the field, we point our thumb in the direction of the velocity, and our palm is pushing up. Okay, so the force on this charge would go upward. Here it is again. Fingers away, thumb to the right, palm pushing up. Now realize that as soon as the particle starts deflecting, it's moving in a new direction. So you have to adjust your hand accordingly. And what the particle will actually do is follow a circular arc up until the point where it leaves the magnetic field, and then it will travel once again in a straight line. All right, so try a few of these. Here we have a magnetic field going from the ceiling to the floor. So the north of the magnet is up here, the south of the magnet is down here. It's a negative charge this time, so you'd use your left hand. Fingers point toward the ground. Thumb, make sure you make a right angle. And the palm is facing toward the camera. Just like that. Fingers follow the field. Thumb follows the charge. Palm pushes toward you. So this charge would be deflected in this positive Z direction. Okay, you're going to have all kinds of different ways you might have to contort your hands. Again, right hand for positive charge, left hand for negative charge. Okay, this time it's kind of weird. We've got the particle moving in the Z direction, meaning it's coming toward you. So you're going to use your right hand because it's positive, thumb toward you, field toward the right. Hopefully you see your palm is pushing down, and actually that was the wrong hand. We got to use our right hand. So again, thumb toward you, fingers to the right, palm is pushing up. this would deflect in the positive Y direction. Okay, just like that. Thumb is pointing out of the board, fingers are pointing to the right, palm pushes up. Okay, so you can try a few of these things. Make sure you know how to orient your hand. Right hand for positive charges, left hand for negative. One of the places where we see this, that is a charge being deflected by a magnetic field, are the charges from the solar wind. As they approach the Earth and interact with the Earth's magnetic field, they're going to be deflected according to the hand rule. Positive charges you'd figure out with the right, negative with the left. They're going to produce spectacular views near the north and south poles, and these are known as your northern or southern lights. I have one problem online I'd like you to try just to make sure you know how to use the hand rule, and also so that you show me that you know how to do the calculation. So good luck. Stop in McCully 1 if you need help.